All right, thanks everyone for coming up. This is a talk I'm going to give to talk a little bit about how to use Rust from Python, and also how we built our Python stream processor called Bytewax that has a Rust engine and a stream processor. So I'm Zander. I'm the CEO and founder of Bytewax, which we'll talk more about. As I said, it's a Python stream processor with a Rust engine. Before starting Bytewax, I worked on data science and machine learning infrastructure at GitHub and Heroku. So what we're going to cover today. First, we'll do a little context setting. Don't want to assume any prior knowledge. Then we'll talk a little bit about the emergence of Rust and why it's nice or fun or interesting. We'll compare some Rust and Python code, and then we'll write a little function with PyO3 and use it from Python, and then I'll talk about how we use it with Bytewax and what Bytewax is. Okay, so I could be the only one in this room, but before I started Bytewax, I really saw Python only from the surface. It was easy to use, flexible, readable language that had all of my favorite libraries. And as we all tell each other, it's also slow, unsafe, lacks strong typing, is difficult to scale and maintain, suffers from the GIL, and pickling crazy objects is everyone's nightmare potentially. And this is all true, of course, but everybody's doing it. So why is Python one of the most popular programming language? Is it its flexibility, its readability? What makes it such a strong programming language for people getting started and even people with a ton of experience, and all of us in this room? Well, my reasoning is that Python's really just a portal to another language, C, C++ notably. In fact, that's a feature of the language and not a bug. If you look at the early letters and memos from Guido, he explains how he wanted to write Python so it was readable like a prior language, but that he worked on called ABC, but he wanted it to appeal to the Unix C hackers. And so for this reason, Python was written in C explicitly so it could interface with legacy C libraries. And there's tons more we could talk about there, but for the purpose of this call, we can say that, or for this talk, I spent too much time on Zoom. We could say that Python is kind of like the king of foreign function interfaces. If you don't know what a foreign function interface is, it's kind of a nice way of saying one programming language saying to another, hey, I have this data and I want you to do this set of instructions, go do it, and then tell me what you get back. And most of the languages you all use on a daily or weekly basis probably use FFI or beyond that, but use C or C++ under the hood to get around some of those nasty little bits of Python. SciPy, NumPy, database clients, visualization tools, machine learning, AI, etc. What is happening right now that was kind of interesting is a lot of libraries or newer libraries are being developed with Rust or porting over to Rust. You've probably seen some of the Polars folks around here. There's also people at PyData who might be here, I'm not sure. There's Rust used at Hugging Face, some of the tokenization libraries. Bytewax uses Rust, et cetera, et cetera. UV and ROF, if you're into the latest development tools, those are great. They're written in Rust as well. On and on and on. And it was recently shown as the most admired programming language by developers. So why do developers love Rust? Being the CEO of a company, I do some hiring. And if you've ever opened up a job for an engineer that knows Rust, you get a ton of inbound. And everyone's like, oh yeah, I use Rust in my hobby projects. I've done a lot of Rust development in my hobby project. And what I'm really looking for in my next role is to do Rust professionally. But I have zero Rust professional experience. So a lot of people admire it, but they haven't had an opportunity to use it yet. That being said, we do see Rust adopted in many interesting places, from the Linux kernel to the big clouds, Hugging Face, Big Metropolis. The list goes on and on. You've all heard about Rust. I can probably stop talking about you hearing it. But why do people choose to use Rust over C++ when there's already so much prior art, especially in the Python ecosystem, of using those tools, and there are a vast number of libraries developed to interface with those languages? Is it because it's trendy and exciting? We all love getting on the latest, greatest hype train. Well, probably not, if also companies are actually adopting it. It's because it's performant. Rust is for sure performant, but is it as performant as C? Probably not, so maybe that's not the only reason. Or is it the developer quality of life? And I'm here to argue that the developer quality of life is the reason that every developer admires it, as well as companies are adopting it. If you can get nearly the performance of C with a developer quality of life that lowers the amount of time you spend debugging code and writing code, well, then everyone's going to be happier. So, quick reason on why the developer quality of life is nice with writing Rust. It largely comes down to the compiler and a couple design decisions that the language team made. So you'll probably heard about memory safety, blah, 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 blah. So there's a concept of ownership where in Rust each value can only have a single owner at a time, and so the compiler can check to make sure there's no collisions there. You also have a borrow checker, which kind of helps in the same way. What you can think about here is that you don't need garbage collection, and therefore you have, because of these concepts, and so therefore the compiler can kind of tell you if you fucked up or not. You also have strong static typing, which some people like or some people don't. I'm in a group of Python developers, so you can probably draw a line down the room, and half of them are going to go YOLO type, and the other half are on the type train. I don't know. Static typing can be nice when you're developing. Type hints are great. The other thing is concurrency safety, which allows you to use threads in a nice way. Okay, I'm going really fast because I have a shitload of slides, and I don't know if we'll get through them all, but we're going to compare Python and Rust, and we're going to do a very fun little CS example where we compute the nth Fibonacci number in the sequence. We're going to do it recursively. It's a nice example because it's O to the n complexity, CPU bound, not IO bound, and it's pretty simple to write. So it fits on the screen. So if you're not familiar, what we're doing is we're giving it like an integer, and then we're going to compute recursively in this little fibn function what the value is of that nth number in the sequence by adding the prior two numbers. So we can run this thing and do a very rudimentary evaluation of how long it takes to run. Don't use this if you're trying to make sure this is the difference between these two, but for this purpose it works. So take 1.13 seconds and 7.3 megabytes of memory. Okay, so keep that in mind, and we'll go look at the Rust one. So you had all seen Python, so you kind of know Python. Rust is, the first thing you might notice is that it's actually quite readable as well. So that's nice. You'll notice that we specify the types of our variables down below, and you might see some differences. We don't have any of the funky ampersand things or question marks in this that come up in Rust, and I'm not going to try and teach you Rust in this, but for the purpose of this, it does the exact same thing. So we run this with our little time utility again, and the same integer of 35, it gives us the same value. It did it in 80 milliseconds and used 900 kilobytes. So resulted in a 14 times speed up, and it used about 1/8 of the memory in Rust. Okay, so why is that? Compiled versus interpreted primarily. So when you compile the code, you can optimize it so you have faster execution. Interpreted language with dynamic types has a lot of overhead. As you have more and more function calls, you're going to have more and more overhead. So that's exacerbated over time. So that's cool. We all are on the same page at this point in time. Rust is faster than Python. Okay, great. But what if we want to take advantage of Rust from Python? There's a project called PyOxide, which is really cool, and you could take advantage of in your day-to-day job, especially when you want to ship off some data and do some arbitrary instruction on it or computation and then bring it back. It makes it very easy to interface that. It also has the ability to run a Python interpreter inside the Rust runtime, which is kind of cool too, and that's something we do at Bytewax. It's maintained by some of the folks who work at PyData. David Hewitt, he's given a bunch of talks. If you want to learn how PyO3 actually works, you should probably watch his talks. He gave one at PyCon just this year. Okay, so what does it look like to write some rusty Python or Python PyO3 oxidized Rust? I don't know. So this is the exact same code you were looking at before, with some changes. So it's not the exact same code, but the function itself, where we're doing the recursive Fibonacci sequence, is the exact same. But what you do see here that's added is we have a PyModule, what's called a macro at the bottom, and then we have a PyFunction macro at the top. And we have those two additional pieces of code. One is because we need to use that as the entry point instead of what we're using in the prior code. So what we're doing here is we're basically the macros will, when we compile this, the macros will basically some instruction set that tell this library how to bind to the C API in Python. So in the Py module Fibonacci PyO3, this is going to be where the module we import in Python, and we've given it Python, and then we've given it we've specified a variable that's of a Py module type, and then we can add the function or the capabilities to that module, and then we're returning a Py result, and that's to catch exceptions. And inside that, we've added a function where we've added a Fibonacci function that receives an integer, and in that Fibonacci function, we're returning a Py result that's typed. So cool, we've written our code. Now how do we use it? So the Rust code needs to be compiled. There's a tool called Maturin that we use. It's developed and maintained by the same people who work on, or some of the same people, I guess I should say, that work on PyO3, PyOxide. And Maturin will build that, compile that code into a binary that you can then use as a Python module. So this is me just using Maturin to release it in a development scenario so that I can use it locally. And Maturin builds one of the fun or maybe not so fun things about writing a PyO3 library, and this kind of for many languages as well, but you've got to build it for every target that might run it. So you'll have the matrix can blow up pretty quickly of different architectures and different operating systems. Once we've built it, now we can use it. So it's pretty straightforward. This is cool. But now we can just import the Fibonacci PyO3 and we can run it. And if we do that, we can see that we're running here Python fibrs.py, so that's the PyO3 version. That's our Rusty Python. We're giving it an integer of 35. It gives us the same number, and its completion was in 130 milliseconds, but it used 7 megabytes of memory, which is probably Python interpreter overhead. So we got a 9x speed up by passing this into Rust. So that's pretty awesome, right? Okay, now, yeah, sorry.
Sorry, is it okay to ask a question? What's the
relationship
between PyOxide and Maturin exactly? Is one a library and the other one's a CLI, or what?
Maturin is a build tool. So that's for compiling the Rust and packaging it up into a Python module. PyOxide is the Rust crate that you use to decorate your Rust code. And so it's like the API sort of, and those macros that allow Maturin to have the instructions to compile it into and package it as a Python library. So they kind of work together. Maturin was developed in order to build and release PyO3 Rust code. All right, so this is Bytewax Chonky B. If you've been by our little booth, you can get your own Chonky B with crustacean claws. So we're going to switch gears and we're talking about how we build Bytewax. So this is a little bit more like story time, if you will. For those of you who aren't familiar with Bytewax, it's a distributed stream processor for Python that uses a Rust engine for real-time data transformations. Well, what the heck does that even mean? I don't know what a stream processor is. Essentially, it's the semantics to describe how you would connect to an input source and consume from that input source, and then transform the data using Python libraries, so we plug into the Python ecosystem, and then write that out to various sinks. And it's designed and architected to work well with streaming data. So you can do stateful transformations like windows and aggregations. You don't have to worry about ordering or distributing stuff across processes and workers. Bytewax sort of handles that for you. Bytewax runs as a Python, just like a Python script or a Python service. You can deploy it into any environment that Python would run. The reason that Python exists, or sorry, that Bytewax exists, is we wanted to provide a way for data scientists, machine learning engineers, who oftentimes have to do real-time transformations to support real-time inference, on streaming data. And so we wanted to be able to plug in the Python ecosystem, and in order to do that with the existing tools, do it in a way that plugged into the whole developer ecosystem as well. And there wasn't anything at the time that did it. We didn't want to just abstract Flink and Spark, which are the incumbent tools that you do to use stream processing. So this is kind of like a little snapshot of what it looks like. You're writing entirely Python code. So you're passing Python functions, and you wouldn't really know that this has a Rust engine underneath it. Just like if you use those C++ libraries. So just reiterating, we wanted to empower data science, machine learning engineers, and Python developers to build real-time applications. We wanted to fit it inside the Python ecosystem, fit inside their workflow. Can I run it locally? Can I write tests against it? How do I deploy it? Does it fit into the current deployment methods, which is something that's really hard to do with Flink currently. And then once again, we didn't want to just abstract and give you a hosted version of Flink. When we decided on what we were going to build to support this problem, or solving this problem, we discovered a project called Timely Data Flow, and this is where our foray into PyO3 started. So Timely Data Flow is a Rust crate. It's a processing engine. It's based on a project called Naiad that came out of Microsoft Research. It's currently used at Materialize as well as Bytewax, and there are some other companies out there that use Timely Data Flow as a distributed processing engine. The benefits for us for using Timely Data Flow, although we had to figure out how to use PyO3 and bind or nicely make Python and Rust work together, was that we didn't have to build a distributed processing engine from scratch, because that's really hard to do. Timely Data Flow also gave us some primitives that allow us to express these transformations with operators, and had some great capabilities like scaling, local execution, and stateful computations. So quick little, check this over. So you get a sense for what I'm talking about. We'll just look at the README quickly. So people are interested in Timely Data Flow. It's a pretty cool project. It's fairly academic. It's not really production ready, so that's part of the reason why we ended up building around it. It's really simple. It can be really simple. You're basically like iterating over stuff. And so the simple example is like turn this range of integers into a stream and then inspect them. It's like, oh, that's so simple, that's so straightforward. It can also get more complex, and streaming does get more complex, and that's why the primitives are important. Like, for example, what if we wanted to distribute all of those numbers across multiple workers, and we cared about which order they completed in? Or maybe all of those numbers were keyed on a certain value, and we wanted to aggregate, and we needed to make sure they went to the right workers. So things can get really complex really quickly. Timely gives you those primitives to do that. So all of this is to say that the very early Bytewax was using PyO3 to bind Python to Timely Data Flow. So we really exposed a lot of those Timely Data Flow concepts in Python, and we feel like, hey, Hacker News, check it out, look at us, give us some stars. And we got some stars, and it was cool. Like, people like this. There's a reason maybe we should build this library and build more on it. What we do with PyO3 for Bytewax is more than just bindings to the operators. So the more simple part of what we did was just take the Dataflow API, the Timely Dataflow API, and the core operators, and make the PyO3 bindings to those. But then what is more complex, or maybe more interesting, maybe it's not more complex, it's definitely more interesting, is inside of each one of those operators, we wanted people to be able to run Python code. We wanted to create a Python native experience. We didn't want to make a DSL into a completely like Rust. So like if you wanted to do a sum, you had to use our .sum or whatever. We wanted you to be able to write a map, use a map operator to write some sum function. And so, or I guess you'd probably use an aggregation one. But anyway, regardless, we wanted to provide you the ability to run random Python functions inside of these operators. And so PyO3 gives you the ability to also run the Python interpreter, like I said, and then you can run arbitrary Python code in that Python interpreter. So that's some of what we did. The early days gave us a lot of benefits, but also had a lot of sacrifices, and we've kind of been building from there. First is we exposed all the primitives of Timely, which if you go and look at what Timely is about, there's like a whole book, and it takes a long time to really understand what exactly you're getting out of it. And we were exposing a lot of that to the users, so that made it really difficult for people to actually move beyond running a simple example. It also didn't provide any production features, so there was no recovery. You couldn't rescale your workers, didn't have any tracing, et cetera, et cetera. There were no windows, there were no joins, it was missing a bunch of operators that we thought were table stakes. I mean, it's hard to imagine doing much in the way of stream processing without the ability to a window or a join. And there were also no connectors. Connectors being input and output sinks and sources. So you had to write your own. And in order to write your own, you had to drop into Rust. And so that was another big problem we had, is that, hey, if anyone wants to customize this, okay, that's fine. Just go fork the repo, download Turin, figure out how to build the thing yourself, write some Rust code, then write some PyO3 code to make sure that you can call that Rust code properly from Python, package it up, distribute it. It's not so hard. So this is what we finally ended up with, and this is the kind of ultimate Bytewax we have today. And so we made the decision to pull the very base parts of timely data flow operators into Python and then build all of the operators on top of that. So the easiest way, so this way folks could easily take a Kafka connector that we've developed or a map operator, and they can modify it slightly for whatever their workload needed. Because it turns out like most situations, people wanted something slightly different. So this was our way of getting around the fact that it was going to be a really bad user experience to continue to put everything into the Rust layer. We had to make some sacrifices to make that all work, and some of the sacrifices we had to make to some of the trade-offs we made in order to provide this customizability was that obviously there's not as much of a focus on performance. So the whole first part where I was like, Rust is really fast, we actually don't get that much benefit because we made the trade-off between we want customizability and extensibility over performance. And the reason we wanted that over performance was we're never going to be able to compete in performance, because if you really cared about performance more than anything else, you would just write Rust code yourself. And what our users cared more about was the time to production and time to value, and the iteration speed with which they can develop. So, in summary, PyO3 is an amazing project, and there are still some gotchas when you're developing any Python library that interfaces with another language. So because we were running the Python interpreter, you still had to manage the GIL. And so that's one of the reasons we don't get some of the benefits that maybe we would get from interfacing with Rust, because we still can't use threads in most scenarios, because we had to lock or grab the GIL when we're going over to do that work in Rust. Another thing, Rust types do not always equal Python types. I think everyone probably knows that. I mean, the other decision we made, I don't know if some of you went to the other stream processing talk today about CSP. We're generally applicable library, so we're not very constrained in our use case and applications. And so we wanted people to be able to use random Python objects. And in order to do that, we had to serialize random Python objects. So we used Pickle. And so there's there's all these trade-offs. Handling stack traces. So, we've had multiple iterations of this. One of the engineers who worked on this is sitting in the back of the room, and if you want to talk to him, he'll be at the booth after. But passing the exception back correctly in a way that the user could actually interpret it. Our most commonly compared tool is Flink and InFlink. It's PyFlink. If you've ever used PyFlink, the stack trace is an absolute disaster, so you never know what's going on. So we wanted to make sure that experience was better. So that's kind of hard because you have multiple layers where you have to pass things back. And so Otherwise, like the Rust panic would cause you to just show like a random Rust line, and you wouldn't know where in your Python file, and if it was 250 lines or 1,000 lines, you wouldn't know where in your Python file you actually had that issue. So that's something to be aware of. Distributing the software is also something that's important. PyData Global 2 years ago, I did a workshop using Bytewax, and it was like run in Google Colab. And the morning, right when I was starting the workshop, they changed the distribution, the Linux distribution for the Google Colab, and we didn't have the binary for that. So when pip went to go look for the Rust, went to go look for Bytewax, and would return an error that Bytewax didn't exist. And so like half the class, or like half the workshop group, had Bytewax, and the other half couldn't install it. So that was like a big pain in the ass, because I couldn't just say like, oh, just like build it, like, no, I had to like show people how to like download Maturin and then download Rust and then build it. So it was kind of a disaster, but that's one of the things that's kind of funky about distributing software. This thing's getting louder and louder. And the other piece was modifying the underlying code. Like this was way more of an issue than we initially expected. It's really hard to attract contributors when, in order to add anything to the library, you had to go write Rust and learn PyO3. And some people want to do that, of course, and you can go do that, but it doesn't make it feasible for everyone. Also, if you're like using this internally, like I said before, packaging up it yourself and maintaining all of that is kind of a headache, where if it's just Python, you can just go override a class method or whatever you want to do. I have no clue how long it took, or if there's a thing, but I thought I had like 43 slides, so I went really fast. I don't know how long it took, and this is the end. You can check out Bytewax, bytewax.io, or github.com/bytewax. And actually, there was one other thing I was gonna show. This was like the early days of what Bytewax looked like, but it's not that fun for everyone to look at. But you can see the bindings to the operators. That was all I was gonna show, and I was gonna kind of show people how we create Py methods, and then within the data flow, you have the different operators, and you pass a callable, and that's kind of what we passed a function. You could kind of think of Bytewax as like a giant chain of UDFs. It's kind of what we do, but I would never say that like explicitly that's what it is, because I hate UDFs and they just give me nightmares. But that's sort of what it is. Yeah. That's it, that's all. I think I went way faster than I expected. I'm sorry. I don't know if anyone has any questions. Otherwise, I can show you what Bytewax looks like. I can show you our commercial product. Running some, we'll do some live stuff here. This is our platform. So we have the open source project, and then we also have a platform. The platform is kind of like your orchestration and governance layer, so you can see all your data flows. Let's go and look at one of these data flows, and you can kind of see, it probably gives you a little bit more of an idea of what I'm talking about. So a data flow is a programming model. You can kind of think of it as like a directed graph. The like bit under the bit about it that's like important though is that it's a data parallel paradigm. So every worker is able to run the same operations, which has benefits and drawbacks. Some of the benefits are if you're not running multi-process things, or you don't have to exchange data because it's keyed and you're aggregating, you don't have to pass data around between tasks. So if you have heterogeneous workers doing tasks, task parallelism is the other way you could go. You might have more data being serialized and shuffled across different processes, which is a lot of overhead. Anyway, look at, this is like probably really small. All right, so let's pretend we're writing a data flow. So I mentioned how Bytewax is a API and semantics to describe how to connect to sources, transform data, and bind it to sinks. So you can write and we have an emphasis on customizability. So we expose the API to write your own custom connector, where you can determine how often you're going to pull, how much data you're going to retrieve every time you pull, how you're going to track progress, which is the snapshot, how you're going to close, all those sort of things. So an input is made up of two parts in Bytewax. You have the source itself, which is basically a set of instructions of, hey, I have this many parts. Think of it as like you're splitting your file, you're splitting your stream. I have this many parts that I want to distribute across my workers. And then Bytewax will call, so that's Bytewax calling list parts. Here we're just doing product IDs, so those are crypto pairs, cryptocurrency pairs. And then build part actually sends, or sorry, actually calls on each partition with the key that you're returning from the list parts. And then you're building the actual partition, and the partition has the instructions on how you're going to read the data. And here we're actually using a batch async, so we're batching up an async WebSocket that's Coinbase. And so whatever you receive from that WebSocket, you're going to pass out for each batch. And there's other like methods in here that I'm not overriding. The code, I'll skip on this, but this is the data flow part. So the way Bytewax works is you create a data flow object, and then you're creating a new stream handle. So each operation you do creates a new stream. That's the easiest way to think of it. So in the first one, we're using an input operator. So that's our operation, it's just input. We're passing it a Coinbase source with all of these keys, and we're passing it the flow object. So now we have a new stream handle. So think of it like a generator. I mean, everyone here knows what generators are probably. So like you can think of input as a generator that you could call next now. That's the easiest way to describe it, I think. And then you can add successive steps by passing that stream to another operator. An operator takes a step ID, takes a step ID, takes a stream handle, and then takes a callable. So this can be a function or a lambda or anything like that. And Bytewax under the hood is based on what the operator is. It's going to execute that function. So if you're doing, this is a stateful map step. So one of the things about stream processing that gets tricky is state. Like you need to know what happened prior. So that's what state is. And so in our order book, state is the order book. If you're not familiar with what an order book is, it's all the asks and bids in an exchange. And so what we're asking Bytewax to do is maintain this order book and update it with each new value we get, and then summarize that update. All of that up here is actually the logic. We'll ignore that for now. And then we're adding another successive step. So here we had our stats stream. We're going to put our stats stream in the filter operator, and then we're going to write a arbitrary Python function. So this is what's actually running in that Python interpreter in Rust, and that's just computing this whether or not the spread is over. Started running. There's probably a lot of output here, but here we can see the output from that, and we have our currency pair and spread, and we only have one process on this, but we could edit that data flow, and we could increase the number of processes, so we can scale this up, or we could do workers. You have workers per process, and then you have process as your parallelization hooks. You're going to save the changes, and this is going to redeploy that data flow. It's going to take some time to run. It's still starting up, but at some point, it'll be, well, it's going to take some time to kill it, and it's going to take some time to redeploy it. Under the hood, this uses Kubernetes, so we have our own operator that's listening for the events, and then modifying all pods. So here we go, now we have, oh, this is still workbook 0, so we still don't have 2 workers, but at some point this will be redeployed, and we have both those processes running. Maybe I have another one that has more than one. Here we go. This is another data flow. We can ignore that for now, but I just wanted to show. So when you have multiple workers, you'll have each worker doing different things. This thing's just failing to connect to Confluence. That's not doing anything exciting. But yeah, that's it. questions at the end.
I'm still trying to understand sort of how it all got started. Like, usually, like, you basically said near the end, we're going to let people write their own Python functions and not burden them with writing Rust code.
Yeah.
But you started with Rust engine data.
Yeah.
So, like, why do you mix them with university? Why do you start with Python versus Rust?
Yeah. Well, I did mention it is really difficult to make a proper functioning distributed processing engine. And so we wanted to be able to move fast enough. We didn't know if this was something people were truly going to be interested in using. So it was a way to kind of delay that development. We have been recently developing our own engine for this that we can sub out because there are some data flow principles that we don't actually like, that don't mesh up so well. So that it was mostly in the essence of speed and effort to determine if there was
So actually, like almost like a prototype that ended up being a product.
Yeah, once we got the prototype out there, we realized it was more than enough for what most people needed, but there was a bunch of things on top of that they actually wanted. The real reason people don't use timely data flow today is because there's no recovery, there's no scale, there's no rescaling, there's no inputs and output sinks, and it's hard to write your own operator. And you have to understand the timely data flows logical timestamp and how that affects everything you're running.
And do you have any plans to maybe somehow make the Python function optimize Rust code but not on that?
Well, I
asked Polish the same question, by the way, they said no.
Well, the interesting thing is when you run that Python function, it could be it could be using Rust or it could be using C or C++, because it's the C. If you used polars so say you collected or aggregated stuff into a list, and then in the next step you wanted to average that or whatever, and you had put it into a polars data frame and you did polars average, then it would use Rust there.
Yeah, you send a Python interpreter inside of Rust to delegate to
exactly. But it's seems so scary, but I mean the point of the first part was we do it every day, all the time. We're always so it's not. But yeah, we have thought about we could optimize a lot of things. But then your bear mentioned a DSL, and you get more and more declarative and more declarative, and then you're hey, here's a YAML file, describe yours.
Yeah, we backed off on that approach.
Yeah. Here's a YAML file, describe your stream processing.
Since you said you had to sacrifice on the performance aspect of Rust, now that you're going to be building a new engine, are you going to continue using Rust?
Well, because we still run arbitrary Python code and we still deal with Python types and objects, there's not that much we can really do. So the overhead of maintaining a Rust code base and not having people to easily contribute, and some of the timely data flow semantics, we could run it in whatever we wanted, but it might make sense to, actually this iteration, the experiment we're running is in pure Python. And that way, actually the reason we're doing that is because then you can compile it from LASM. And that way people can run it inside of a bunch of the streaming platforms offer little LASM thing you can run to transform and stuff. So it's easier for people to run on trusted code and compile it. Allegedly, I don't know anything about it.
You may have answered this before, but did this start in a particular domain and generalize after that?
Well, it started, so the whole story behind Bytewax is I left GitHub to build a machine learning platform that was specifically for real-time machine learning, because it was a friction point we had when I was working at GitHub. And we didn't actually have the idea of making a stream processor. So it was focused on machine learning, and it was more focused on inference. And this was before inference became a hard problem. And so when I was showing everyone what we built, they're no, you know what, inference isn't a problem. I just run my model in Flask or Fast API. What I really want help with is data processing for features to get to the model. So we made it explicitly for feature transformation.
Okay, thank you.
Seems like the boundary between PyOxide is pretty high. I guess how do you you're working on a project, how do you make that decision? Because it's actually
if your Python code wasn't complete.
No, it was like, it was literally just can't run.
Like, yeah, say you have like, let's say you're doing a problem like, you have a predefined route of GPS coordinates, and you want to like match proximity of another like route going near it, like a Strava or like a GPS routing system. That's a super computationally intensive thing, and if you like drop into Rust, you might be able to make it finish, and it wouldn't in Python. Or like some graph problems, you know, when you're like, well, the reason I did a recursive thing is like, say you have a recursive thing, and Python has a ton of overhead, and the more recursion you do, the more you're going to be having the overhead of the dynamic typing and the interpreted language, and so that could be an area where you just like decide. If it's I/O bound, most languages are optimized for I/O, so you might not have any, you know, reason to do that. There might not be any performance trade-off benefit.
I have a question about PyO3. So, how flexible is it to use Rust crates that exist? And like, are you able to just pull that into Rust and just put the decorators on some of the functions and use it, or
I don't remember the name of the library. We had like an intern, and he did this, but I can't remember. There's a blog post on the Bytewax blog. Let me see if I can
because
find
a
it.
lot of stuff may already exist in Rust that may be beneficial for you to use, but
I think he did this, so this is an example of doing that. I don't remember what it is. So this is he took a Rust crate and he wrote bindings to it. So
okay. So this is his example of rebuilding a Rust crate for the use in Python.
yeah, someone else. Going now?
I don't
This is
know.
the end.
Yeah. Or
Oh, okay. So yeah, there's some work because you basically have to go into, create a Rust file where you're like explicitly saying every function or everything you want to expose and kind of decorate it.
Right. Okay, cool.
And managing types and managing exceptions and panics and all this sort of
Yeah,
things.
so it's not as like import the crate, wrap it, the function, and then you're almost rewriting it for use with PyO3.
Yeah, probably
Rather
the
than-
better thing to do would be like if there's a very explicit task you want to do that invokes that crate. And you go and write the Rust code that does that. And so all you're handing from Python is like integers of data, and then it does the one thing. So you haven't exposed that whole crate.
You make up a small function that is injecting itself into the Rust crate. Essentially, just the small pieces of data you need to use in Rust, and then like a crate takes over from that. I mean, cool.
That would be the least amount of work.